In this video, we will see about the types of AC voltage regulator. What is an AC voltage controller? Basically, it is an AC to AC converter. That is, it converts fixed AC voltage to variable AC voltage, but without changing the frequency. You cannot change the frequency in AC voltage controller. You can change only the magnitude. How to achieve this AC-AC conversion? You can use bidirectional devices. So you can use two thyristors in anti-parallel, or you can use a Triac, which is a bidirectional switch. There are two types of AC voltage regulator. One is called phase control regulator. Another one is called the on-off control technique. So in phase control technique, you can use either SCRs or Triacs, and the devices are turned off by natural commutation. In on-off control, you have to use either forced commutation for turning off the SCR, or you can also use the other self-commutated devices. In phase control AC voltage regulator, there are two types: half wave AC voltage regulator and full wave AC voltage regulator. So in half wave AC regulator, you can see there are two devices in anti-parallel. One is a thyristor and the other one is a diode. So we know diode is a uncontrolled device. So in this case, you can control only one half, that is the positive half can be controlled, while negative half is not under our control. If you see the circuit of full wave AC voltage regulator, two thyristors will be connected in anti-parallel. That is the difference. Let us see the operation one by one. So first one, half wave AC voltage regulator. So here we have seen one thyristor and one diode is there. So you will get a controlled positive half cycle, whereas uncontrolled negative half cycle. You see this diagram. So this dotted line represents the supply voltage waveform, that is a Vs, and V0 is drawn over it. And for thyristor, so during positive half cycle, so this is the positive half cycle. During positive half cycle, this thyristor will be forward biased and it will get turned on only when gate pulse is given. So that is the firing angle alpha. So alpha is given here. So thyristor start conduction here. So it conducts till pi. At pi, it gets turned off automatically. So you can see the T1 duration from alpha to pi, T1 device will conduct. During the negative half cycle, there is no problem because it is a diode. So during negative half cycle, D2 will be forward biased and it conducts. So during negative half cycle, D1 will conduct for the whole cycle, pi to 2 pi. And again, after alpha, T1 will conduct. So V0 and I0 are in phase because it is a resistive load. Okay. But the problem with this circuit is that you can see here, you see the output voltage waveform. Here from 0 to alpha there is no output, whereas negative half cycle you will get a complete output. So the waveform is not satisfying the symmetry. So when there is no symmetry in the waveform, you will get more harmonic components. So this introduces a DC component into the supply side as well as on the load side. So this circuit is rarely used because always our output waveform should be symmetrical. Both positive half cycle and negative half cycle should be symmetrical so that you can reduce the harmonics. Or when both positive and negative half cycle are symmetrical, even harmonics will become zero. Next we will see about full wave AC voltage regulator. Here you have two thyristors connected in anti-parallel. So you can see The operation is same as the previous case except that during negative half cycle T2 conducts. So you are able to control the output voltage in both positive half cycle as well as negative half cycle. So T1 will be given gate pulse here, T2 will be given gate pulse here. And V0 and I0 are in phase because it is a resistive load. And this circuit is called a phase control AC voltage regulator because you are able to control the relation between the supply voltage as well as the output current. So the supply voltage starts 0 starts here, whereas the current starts here. So since you are able to change the relationship between the Vs and I0, it is called a phase control AC voltage regulator. And this is the widely used method. So let us see the operation of the full wave AC voltage regulator. So during positive half cycle, this is plus, this is minus. So T1 will be forward biased. So you can see here, this is the supply voltage. Gate pulse for T1 is given at alpha, and for T2 you have to give the gate pulse during the negative half cycle, that is at pi plus alpha. And this is the I0 is the output current, Is is the source current. So during positive half cycle T1 will conduct. So when it is given gate pulse, T1 will conduct and this will be the current path. So now you can see here I0 is 0 till alpha, and at alpha it follows the source voltage waveform because it is a resistive load. Okay. Now during negative half cycle, when you give the gate pulse for T2, Thyristor T2 will conduct and current flows in the opposite direction. So you can see here I0 direction is reversed. Okay. Now this is the voltage across T1 and this is the voltage across T2. So whenever a device is conducting, the voltage across it will be almost 0. Okay. So that is represented by some negligible voltage drop. So when T1 is conducting, that voltage you make it as 0 or a small voltage, either 1 volt or 2 volt. Okay. And the remaining period it should follow the supply voltage. So this part T1 is not conducting, so you follow the supply voltage. When it is conducting, it is almost 0, and in this period you should follow the supply voltage. Okay. Similarly, for drawing V2, that is during this period V22 is not conducting. So what is the voltage across that? That will be negative of this one. That is minus Vs will be applied across T2. So minus of this one, and when it is conducting, since both the devices are in parallel, whatever voltage you are getting here, that will be applied in this, but in opposite direction because it is connected in anti-parallel. So you can draw all the waveforms easily. So this is the device conduction period. So T1 conducts from alpha to pi and T2 conducts from pi plus alpha to 2 pi. Let us derive the RMS equation now. So V0 RMS is equal to square root of the total time period. Let us take half cycle alone because waveform is symmetrical. We can take half cycle. So 1 by pi. So the limits are alpha to pi because waveform is available only for this period, alpha to pi, and this is the source voltage Vm sin omega t whole square into d of omega t. So you solve this one. So since it is a square, you replace by sin omega t, sin square omega t by 1 minus cos 2 omega t by 2. So simplify this one. Apply the limits, so you will get this as the RMS voltage. So by varying the alpha from 0 to pi, you can see here alpha is 0 here at this position, alpha is 0. You keep on increasing, you can increase alpha till pi. So by varying this alpha, you can vary the output voltage from Vs to 0. So if your alpha is 0, you will get full voltage. So it will be Vs. If alpha is equal to 180 degree, that is pi, output voltage is 0. So it is 0. So you are able to control the output voltage. Let us see about the power factor. So power delivered to the load resistance R is equal to V square by R. We have calculated what is RMS. So we can calculate the power delivered to the load. So what will be the maximum power delivered to the load? When alpha equal to 0, you will get the maximum power. So when it is 0, you will get Vm square by, so this term becomes 0, this one 0, pi get cancelled, we will get Vm square by 2R. So let us calculate what is power factor, that is real power by apparent power. So this real power is the power delivered to the load. What is apparent power? V into I. So for I can write V by R because it is a resistive load. So power factor is equal to, you can simplify this one. So real power V square by R divided by this one. So if you simplify this one, you will get V naught RMS divided by Vs. So you substitute V naught RMS by Vs here, you will get this as the power factor. So what you have to note down here is that the power factor is a function of firing angle alpha. Though we are talking about resistive load, the power factor is not unity. It depends upon this alpha. So since it depends upon alpha, if you keep on changing alpha, the power factor will vary. So we know it is always desired to have a higher power factor, that is power factor should be unity. So as you keep on increasing alpha, your power factor will reduce. Let us see about harmonics in the waveform. So you see here the output voltage, output current and input current. All the three waveforms from 0 to alpha, there is no output. It is 0. So the waveform is not sinusoidal. So it is a non-sinusoidal waveform. So when the waveform deviates from a sinusoidal waveform, you will get harmonics. So this phase controlled AC voltage regulator, they introduce harmonics. It not only in the output side but also in the input side. So in input and output side, it is introducing harmonics. The other thing is that the waveform is similar in both half cycle, that is positive half cycle is symmetrical to negative half cycle. So even harmonics will be 0 and the waveform contains only odd harmonics. Now let us see how to find the harmonics present in the output waveform. You can apply Fourier analysis. So let us recall what is Fourier series. F of t is equal to a naught plus this expression. So where a naught is the constant term which is given by this formula, and an formula and bn formula is given. The detailed explanation for this one is already discussed in inverter chapter, that is introduction to inverters. So in that you can see about how you are getting all these equations. So let us do the Fourier analysis. So we have an formula. So here the total time period we can take it as t. This t is equal to pi and the limits are alpha to pi. So this function, what is this function f of t? this function. So it is sin omega t. So Vm sin omega t into cos n omega t. So you can simplify this and find what is the An. From that you can find what are the harmonics available. Similarly, you can do it for Bn also. I think you can solve it because already we have derived step by step for inverter the same procedure. Procedure remains the same. Only thing you have to know the formulas for these things. If you don't know the formula or you don't know how to find difficulty in deriving it, just mail me to this email address. I will send you the PDF file. Next is integral cycle control or on-off control method. So in this case, the load is connected to the source for n number of cycles and it is disconnected from the source for m cycles. Let us take an example. You are switching on the fan for some time and switch it off for some time. Then again switch it on and off. So on and off is done, but you can see that even if you switch off, the fan actually continues to rotate for some time. So before it stops, we are switching on again, so it appears to be rotating continuously. Actually in fan, Triac based circuit is used, which is a phase control converter. For example, I am telling that if the mechanical time constant is high in large machines, we can employ this method. That is, you can switch on the machine for some time, then turn it off for some time. So even if you turn off, the machine continues to rotate. And before it stops, we can turn on again. So it keeps on rotating. So this type of control is employed in speed control of motors and heating elements which have a large mechanical time constant or thermal time constants. So in on-off control method also, the circuit diagram remains the same, only the waveform is different. You can see here, this is the supply voltage. T1 is given gate pulse during positive half cycle, positive and positive, you will be given gate pulse, while T2 is given gate pulse during the negative half cycle. Okay. So the output will be there for all the three cycles. So this waveform, supply voltage and load voltage will be same, and you have to remember that there is no phase control. So the waveform is completely sinusoidal, so harmonics will be less. That is why we prefer this method. And after this short period, you have to remove the gate pulses for some time so that the load is disconnected from the source. So no power for the m cycles. So for n cycles we are giving the power, and for m cycles there is no power. And again repeat the same procedure, n and then m. So by this way we are able to control the average power delivered to the load. So we will calculate the RMS voltage. So total time period is 2 pi. So apply the formula, and here you have to calculate what is this, that is on period is n divided by total time period is n plus m into 2 pi. And the limits are 0 to 2 pi. So Vm square sin square omega t. So you substitute this one, simplify this one, and this factor. So you are getting this as a factor n divided by n plus m, that is called duty cycle of AC voltage controller. So it is represented by small k, that is equal to root of n divided by n plus m. So I can write it as Vm by root 2 into root of k, or Vm by root 2 is nothing but RMS value of the supply voltage, Vs into root k. Now we will calculate the power factor. So the power delivered to the load is V square by R. So V square we have already calculated RMS value, substitute it, you will get it. So input for factor is real power by apparent power. So real power divided by apparent. This we have already derived in phase control AC voltage controller. So using that, use the same formula and simplify it, you will get root k. So where k is root of n divided by n plus m. We will find the thyristor average current. So average value you have to find. This is the time period n divided by, that is on period divided by total time period into 2 pi. 0 to pi Im sin omega t into d of omega t. So we are finding only average value. So simplify it. Then we will find RMS, thyristor RMS current. So that is represented by ITR. Same formula except that this part will be squared and you will get a root square value. Simplify this one, you will get the RMS current. So let us see about the harmonics in this one. So this introduces this integral cycle control. The output waveform is sinusoidal. So this method introduces less harmonics into the supply system and it is best suited for heating loads and motor control drives. So the points to remember here are AC voltage controller converts fixed AC voltage to a variable AC voltage without changing the frequency. There are two types. One is the phase control AC voltage regulator, which introduces harmonics both in the supply side and load side, and it has only the odd harmonics because even harmonics and DC component will be 0 due to the waveform symmetry. And integral cycle control or on-off control, in this method the harmonics is less compared to phase control regulator, and this is best suited for heating loads and motor control drives which have more mechanical time constant. So if you like the video, do subscribe to Read Electric Vehicle channel. Thank you.